Now let's look at groups of order p squared times q, where p and q are distinct primes. And let's see what we can learn about these groups using just our Sylow theory results. So, can we find normal subgroups? Let's see what we can calculate about NP and NQ. Note, the idea I'm getting at here is I'm just trying to go from first principles rather than assuming the result we're going to actually discover. So the goal is to try to discover the results. So remember, NP is going to have to divide, it's going to have to either be 1 or q, because it has to be a divisor. And the second case only happens if q is congruent to 1 mod p. Similar, what's NQ going to have to be? Well, it's going to have to be a divisor of p squared. So now you actually have some options. And of course, in whichever case this is, either you have p is congruent to 1 mod q, or p squared is congruent to 1 mod q. So we've got a bunch of different cases to think about. And so we ought to think carefully and try to make some assumptions. So right now we're assuming p and q are distinct primes, but we don't know which one's bigger. Let's assume that p is bigger than q. Also, so that we can actually start to refer to the groups, let's let p be a Sylow p subgroup, and let's let capital Q be a Sylow q subgroup. So let's assume p is the bigger prime. Well, let's look up here. We're in the case where NP is either 1 or q. Q is small though, so is it possible for q to be congruent to 1 mod p? Well, no, because q is going to be an integer that's smaller than p to begin with. So it's going to be bigger than 1 because it's prime. So it's got to be bigger than 1. It's smaller than p. So in this case, q can't be congruent to 1 mod p, which tells us that NP is 1. So congratulations, we've discovered that we have a normal subgroup. In general, I'm sure you've seen by now, our goal in a lot of these arguments is to discover normal subgroups. And a lot of that has to do with the fact that decomposing your group into normal subgroups allows you to change your problem into studying the normal subgroups, which are smaller, which by induction, hopefully you know what the normal subgroup looks like up to isomorphism, and then the quotients, which by induction you know what they look like up to isomorphism. And so then it's just figuring out how to piece them together. So congratulations, we have a normal subgroup. All right, let's move on to case 2. Let's assume q is bigger. And we're going to assume q is congruent to 1 mod p, because otherwise we already have a normal subgroup. What happens with this case? Anything interesting? Well, if NQ is 1, we're done. So let's see what happens in these two cases. Well, again, by the same logic as before, if we're assuming Q is the bigger prime, we can't get this P condition to happen, because P is the smaller prime, and so there's no way to get P to be congruent to 1 mod Q. So we have to be in the case that NQ is congruent to 1 mod Q. So we're either in the case where P is congruent to 1 mod Q, or we're either in the case where NQ is 1, or it's P squared. If it's 1, then we've just discovered that Q is a normal subgroup of G. of size Q. Otherwise, we now have NQ is equal to P squared, which means that P squared is congruent to 1 mod Q. Well, what does this mean? This means that P squared minus 1 is a multiple of Q, but that's also P minus 1 times P plus 1. Q is prime, so this means that Q either divides P minus 1 or Q divides P plus 1. As we can obviously guess, because Q is bigger than P, Q can't divide P minus 1. So it must be the case that Q divides P plus 1. Oh, but Q is bigger than P, so there aren't a whole lot of pairs of primes where this is going to work. I mean, consider 5 and 2. Well, 5 can't divide 3. So for which primes are you actually going to get something like this, where Q divides P plus 1? As soon as Q is greater than 2, Q minus P is greater than 2, this can't happen. So it must be the case that Q has to be equal to P plus 1, and the only pair of consecutive primes is 2 and 3. Which means that we are looking at the case where G equals 12, which the book does separately before this case, but we're going to do it now after. So in general, unless G equals 12, we now see that we have either P or Q is normal in G. So either you have a normal subgroup of size P squared or a normal subgroup of size Q. So where are we at? We've got a group of order 12, and we're assuming that the number of Sylow 3 subgroups is 4. Because we're working with distinct powers here, we have P squared, or 2 squared times 3. That argument we tried before, where you count the number of elements of order 2, or we look at the intersections of the Sylow 2 subgroups, is not going to help us much here. However, it is worth pointing out that we do have 4 times 2, 8 elements of order 3. But my point is, if we assume that n2 was equal to 3, well, we can't use this to count the number of elements of order 2 because these are 3 subgroups of size 4. And so the calculations get a lot more awkward. I mean, are you counting elements of order 4 or 2? Yeah. And they have non-trivial intersections. So the element counting method we were using before doesn't make sense in this case. We're going to have to try something different. And so something different you can try is to consider group actions. So G acts on the set of Sylow 3 subgroups by conjugation. Right now this comes out of nowhere, but this idea of conjugation is used in the proof of the Sylow theorems, as we'll see, and it's often used in a lot of these proofs to show that you actually have a specific group, by actually showing that what you have is isomorphic to a certain group action. So that's the approach we're going to take. So G acts by conjugation. And since there are 4 elements, this gives rise to a homomorphism from G into S4. And one thing we want to claim is that this homomorphism is injective. We note that this kernel is going to be the elements that normalize all the Sylow subgroups. In particular, it's going to be a subgroup of the normalizer in G of P, which is just P. How do we know it's P? Well, because We know the number of Sylow P subgroups. Is 4, which is also the index of the normalizer in G. And so the normalizer is a group of order 3. And so a group of order 3, it must be P. But remember, this K must be normalizing all these Sylow P subgroups. And so it's got to be a subgroup. It's either one or all of P. If it were all of P, then P would be a normal subgroup. So it must be the case that K is the trivial subgroup. And hence, this map is injective, and so G is isomorphic to its image. So now we know that G is a permutation group inside S4. Let's see if we can figure out which permutation group it is. So the point here is that we're looking at a particular group, and we're trying to see if we can actually figure out who the group is. So it has 8 elements of order 3. In S4, there are exactly 8 3 cycles. And so we're looking at a group that has all 8 3 cycles. And there's only one very large group that has that property, among others, but the point is A4 contains the 8 3 cycles. And A4 has size 12. Isn't that convenient? So what do we see? We see that the image of G has the 8 3 cycle, 8 elements of order 3, so its image must have the 3 cycles. So in particular, this image must intersect A4 and contain the 3 cycles. Which means that these two intersect non-trivially, so they must intersect in at least a subgroup. And a subgroup of order at least 8, because there's 8 elements in this set, plus the identity element, so at least 9. That's a bit of a problem because subgroups have to divide the order of the group, and the order of the group is 12. So the only thing that it can be is the whole thing. So phi of G is actually equal to A4. Which means G is isomorphic to A4. So congratulations, in this one case that we couldn't quite figure out, we actually figured out what the group was. It's actually A4. Of course, that doesn't quite answer our original question, right? But it sort of does. When you get down to this level, you now have an explicit group to work with, not just an arbitrary one. And now you can just ask yourself, how many Sylow 2 subgroups does A4 have? So now you're just looking at what are subgroups of order 4? In A4. And we remember A4, well, any subgroup of order 4 can't have one of these 3 cycles because that's an element of order 3. And so what are the remaining elements? You've got this element of order 2, another element of order 2, and another element of order 2. These are the only 4 remaining elements that are not of order 3. And so just let V be that subset, and you check that this is actually a subgroup. So congratulations, you have a subgroup of order 4. And you now know it's the only subgroup of order 4 because any other subset would have to include an element of order 3. And so now we see N2 must be 1. and V is actually normal in A4. And so this is a very long argument, but at the end of the day, we actually did manage to find out that if G is order P squared times Q, then either the P subgroup was normal or the Q subgroup was normal. In general, it wasn't that complicated, but in the case of 12, it got very, very detailed, but we still managed to prove the result at the end of the day by actually showing that either you had a normal subgroup of size 3 or you're actually isomorphic to A4, which has this copy of the Klein 4 group. There is a digression here that in S4 there's multiple, N2 should be 2 if I remember correctly, in comparison, because you have this V, but you also have groups of this form. They're both order 4, but it turns out they're not they're not conjugate to each other, and so they actually form 2 separate conjugacy classes. And there's a lot more. Actually, it's more than 2, because there's several of these type. There's actually 3 like this, so it's actually 4. And it's interesting because this particular one is normal in S4, but the other 3 are not. So it's kind of nice. By doing this calculation, we discovered a normal subgroup of A4 that's a copy of the Klein 4 group, and this one's actually important in this theory of solvability, because other copies of the Klein 4 group in the symmetric group on 4 elements do not have this property.